All right, question number 11 says the speed of an 8 kilogram mass at position A is 6 meters per second. So it's going to be traveling down this way at 6 meters per second. By the time it gets to position B, it actually has increased its speed to 12 meters per second. And it asks, what is the frictional force opposing the motion? So that tells me that there is friction on this ramp. And then obviously we have a 30-degree ramp. So we got a lot of stuff going on here. We're starting at a height of 12. So let's dig into this. I'm going to redraw our ramp here. And if this is my mass, the forces are going to be my force of gravity, straight down, my normal force, up at an angle. Sorry if you couldn't see that. It's moving down the ramp, right? So this is the direction of the motion. So my frictional force is going to be here. And then again, we're going to make my axes. This is going to be in the positive x direction. It's down the ramp, positive y direction. And I'm going to break my gravitational force into its perpendicular and its parallel. Sorry. That's the parallel force. Now, working through this, I'm going to set up my equations, right? The sum of the forces in the x direction is going to be the force of parallel minus the force of friction, and that equals mass times acceleration in the x. Sum of the forces in the y would be my force normal minus my force perpendicular equals mass times acceleration in the y. This is 0. So then that tells me that my normal force equals my force perpendicular, which that is going to equal the force of gravity times the perpendicular, so that's the cosine of theta. All right. What is the frictional force opposing the motion? All right. Now, if we look at our equation for friction, that's mu times my force normal. The one issue is we don't have our coefficient of friction. So even though here we can figure out what our normal force is, we can't then simply plug into this equation because we don't have our coefficient of friction. So while it's good to be able to do this, it's going to end up, well, that's not going to be useful for us. So let's attack this a different way. And there's a few different ways that we could attack this. The one using energy, I think, is going to be the most relevant. And so if we think about this, at position A, we have kinetic energy, and we also have gravitational potential energy, which is based on its height. At position B, when we're down here, we're going to have kinetic energy at B, and our gravitational potential energy at B is going to be 0. We're going to say this is our height of 0 down here. So what should be true is we should have these two should be equal, but if there's friction, they're not going to be equal. So here's let's set up our energy equation. So we did our forces, we did our net force equation, which is awesome. Let's though look at this in terms of energy. So in terms of energy, we're going to have the kinetic energy at A plus the gravitational potential energy at A. It's going to equal the kinetic energy at B. And so that's what should be true, right? But they're saying it's not because there's friction. So I'm going to add this, the kinetic energy at A plus the gravitational potential energy at A equals the kinetic energy at B plus the work done by friction. Friction is going to remove energy from our system. And the other way it would be written would be the kinetic energy at A plus the gravitational potential energy at A minus the work done by friction equals the kinetic energy at B, right? So that's just if we put this variable on the other side of my equation. Both of these are correct, and both of them should give us the ability to figure out what the frictional force is. So I'm going to just go with what we got. So we have 1/2 mv squared at A plus mgh at A minus work is force times displacement, cosine theta equals 1/2 mvb squared. All right. So we can see this is going to be my force of friction. Do we have the mass? Yes. Do we have the velocity at A? Yes. Do we have the height at A? Yes. Mass and gravity. Force of friction is what we're solving for, right? So that's our unknown. We don't have S. And then velocity at B we have in mass. So really the one thing we need is just, okay, so the first thing is we're going to find the force of friction, and then the second thing we'll have to do is find S of the ramp. And we can do that using just basic trig. So that's our process. We're going to get force of friction by itself. All right. So let's give ourselves a little bit more room to do the math. 1/2 mva squared plus mgha. I'm just going to leave this as minus the work done by friction equals 1/2 mvb squared. I'm just going to do that so we can get everything else to the other side first. So I'm going to add work done to the other side, and then I'm going to subtract 1/2 mvb squared. And so it's going to give me the work done by friction equals 1/2 mva squared minus 1/2 mvb squared plus mgha. All right, so pulling out some things that make sense. So mass is in everything. So it's going to be 1/2 va squared minus 1/2 vb squared plus gha equals work done by friction. Now, we know the mass, we know the two velocities, we know the height, right? So that's pretty straightforward. So now I'm going to write it as, okay, force of friction times the displacement cosine theta equals m 1/2 va squared minus 1/2 vb squared plus gha. So then what do we need to do, right? We need to divide by s cosine theta, which actually, you know what, let's do this. What's cosine theta? So the idea on my ramp, this, right, this is my s, right? So S is going to be in this direction. My frictional force is in the opposite direction. So this is going to be an angle of 180 degrees. Okay. And really, we're not going to need that. So this is 180. That makes the cosine of this -1. And really, we don't need that. So we're just going to end up dividing each side by s. And I'll explain here at the end why we can really just drop that -1. Again, this is just looking at the direction of work. So we can divide by S. So, but the problem is we don't know what S is, right? If we look at we know the height, we know this angle, so we can solve for S, and that's what I would do. So we got our equation set up for the force of friction, right? M 1/2 VA squared minus 1/2 VB squared plus GHA divided by S. So we have that. Now let's find S. So I'm going to draw my ramp. I know this is 30 degrees, this is 12 meters, and I'm trying to find this length here. That's my hypotenuse of my triangle. So this is my opposite side, this is my hypotenuse. So that's going to be the sine of theta equals opposite over my hypotenuse, which that's going to be S. S is my hypotenuse. So let's solve for S. So we need to multiply each side by S. S's go away, so I have S times the sine of 30 degrees equals 12. I'm going to divide each side by the sine of 30. And I get S equals 12 divided by the sine of 30. That's going to give me an S value of 24 meters. So then I can take that value, I can plug it into here, and so my force of friction is going to equal 8 times 1/2. What's my velocities? 6 and 12 and 8, right? Okay. 6 squared minus 1/2. 12 squared plus G. Oh, G is 10, not just G. So that's 10 times 12 divided by 24. So a lot of numbers, but not too hard. 6 squared is 36 divided by 2 is 18. 144 divided by 2 is 72 plus 120 divided by 24. It's going to give me 528 divided by 24, which is going to be, the force of friction would be 22 newtons. So again, looking at this question, right, it's a good amount of work, right, but it's simply the idea that whatever energy I have to begin with is supposed to be the energy I have at the end. Well, I don't have the same amount of energy because I've lost some due to work. And so with that, I should be able to then figure out how much force there is by working through that equation, okay? So obviously, the one thing, right, it would have been so easy if they would have just given us the coefficient of friction, but we don't have that, and that's often a number that, you know, is not known. So setting up the idea of energy then can get us through the same type of problem without that value.